So let's see if you can factor these two trinomials here. One's going to be an easy type, the other one's going to be a difficult type, okay? So this is classwork 1, November 29th. All right, see if you can factor this trinomial here. And then see if you can factor this difficult trinomial here. Okay, so see if you can factor those two trinomials, and we'll take a look at those and move on from there. All right, this first trinomial is an easy type of trinomial factor because it has a leading coefficient, which is 1. These type of trinomials were discussed in section 3.2. All we need are two factors of -40, the constant term of this trinomial, that add up to your middle coefficient of -3. So what's helpful to do, which you don't have to, but it is helpful, is to make a product sum little table here. Our product has to be -40 and our sum has to be -3. Now we're going to try to search for a couple of factors of -40 that add up to -3. And if you don't know what they are, and if they don't pop into your mind, if they do, that's more power to you. But if they don't, then you might want to just start making a list of all factors of -40, -1 and 40, 1 and -40, -2 and 20, 2 and -20. 3 don't divide into 40 evenly, 4 does, -4 and 10, or 4 and -10. 5 divides into 40, -5 and 8, or 5 and -8. 6 don't divide into 40 evenly, 7 doesn't, 8 does. Now in this list, which two of these factors sum up to -3? Well, it's certainly not going to be -1 and 40 because these add up to 39. That's not even close to -3. Let's see, which ones add up to -3? You may spot which ones sum up to -3.
Is it -5 and 8?
Now we have to have them sum up to a -3. -5 plus 8 add up to a +3.
5, -8?
Gotta be these right here. These are the only factors that add up to our middle coefficient of -3. 5 and -8. None of these other ones work. They don't sum up to -3. These are the only ones. So therefore, this trinomial will factor immediately into two binomials. And the factors have to be t plus 5 times t minus 8. And we're done. We have the factorization of that trinomial. Or you could have these switched around. You could have the t minus 8 here and the t plus 5 here. Did anybody get that factored correctly?
Yes.
That was section 3.2 in a nutshell. Those types of trinomials, the easy types where you have a leading coefficient of 1. Okay. Now in 3.3, they're the more difficult types to factor where we don't have a leading coefficient of 1. To factor these types, I recommend the grouping method. And that method kicks off by taking the product of the leading coefficient and the constant term. So we take 2 and multiply it by 12. And 2 times 12 gives us our product of 24. And our sum must be +11. Okay. So now we're searching for two factors of +24 that add up to a +11. So let's start listing factors of 24. 1 and 24. Now, -1 and -24 are factors of 24, but these don't sum up to a +11. Two negatives don't add up to a positive, so don't waste your time with the negative factors here. 2 and 12, 3 and 8, 4 and 6. These are all factors of 24. Which two in this list sum up to 11? Which two of these add up to 11? Well, it's not 1 and 24. These add up to 25. It's not 2 and 12. Yeah, these add up to 14. 3 plus 8, I think, works. These add up to what we need, namely 11. So the factors that work are the only factors of 24 that add up to 11 are 3 and 8. We're going to use 3 and 8 now to factor our difficult trinomial. To do so, we're going to rewrite this trinomial as an equivalent 4-term polynomial, where my middle term gets split up and rewritten into the sum of 3x plus 8x. Now we have a 4-term polynomial, and so we're going to factor it by grouping. So we group together our first two terms, and we group together our last two terms. Out of the first two terms, what can I factor out? I can factor out, what can I factor out of both these terms here?
6.
X. And when I factor x out, I leave behind 2x plus 3. plus the last two terms. What can I factor out of 8x and 12? What is the greatest common factor of 8x and 12?
4.
4.
4. When we factor it out, we leave behind 2x plus 3. Now we have a common binomial factor of 2x plus 3 that can be factored out of both these terms. And when we factor it out, there it is. Times, what do I leave behind? X plus what, 4? And that difficult trinomial has been factored. This is called the grouping method for factoring these difficult trinomials where the leading coefficient is no longer positive 1. So those are the type of trinomials that were tackled in section 3.3. Ladies and gentlemen. So again, if you have not watched that video, please do take in the video that I posted on Canvas for section 3.2 and 3.3. Today, we're going to tackle 3.4 and 3.5. In section 3.4, we're going to look at the binomial family and how binomials can be factored. And then in 3.5, we're then going to put it all together, and we're just going to look at what's called general factoring, whereby we're given a polynomial and we're asked to factor it completely. So that's going to be the order of business in section 3.5. All right, so section 3.4 is going to have us concentrate on factoring various types of binomials.
Is it 6.4?
It should be 6.4. I keep saying chapter 3. Yeah, so 6.4 and 6.5. The video covers 6.2 and 6.3. That's the video I posted on Canvas. Please watch it if you haven't seen it before. 6.4 is factoring binomials. And there's going to be 4 main types that we're going to have to learn how to factor in this section. Factoring binomials. All right, the first type here is called the sum of squares. This is referred to as the sum of perfect squares. The sum of 2 squares, and the sum of perfect squares cannot be factored. So this is non-factorable. Non-factorable. Then we run into the difference between squares. This is called the difference of squares. And the difference between 2 squares factors into the product of these 2 binomials, a plus b times a minus b. Or you could have these switched around. You could have the a minus b here and the a plus b here. This is how you always factor the difference between 2 perfect squares. Notice it factors into binomials that differ only by the sign in between the terms. Because of that, we call a plus b and a minus b, we refer to these as being conjugates of each other. So they are called conjugates. All right. All right, so that's the difference of squares. Then later on, we run into the sum and difference of cubes. This represents the sum of 2 cubes, 2 perfect cubes. So this is a sum of cubes. And the sum of cubes does factor. It factors into the product of a binomial and a trinomial. Specifically, it factors into a plus b times a squared minus ab plus b squared. That's called a sum of cubes. That's how it would factor into the product of a binomial and a trinomial. All right, then we run into what's called the difference between cubes. And this would factor in a similar way, a minus b times a squared plus ab plus b squared. This is called the difference of squares. difference of cubes, excuse me, cubes. So these are the main types that we're going to be confronted with in section 6.4. Sum and difference of squares, sum and difference of cubes. Notice the sum of squares again cannot be factored. And the difference of squares always factors into the product of conjugate binomials. And the sum of cubes and difference of cubes factor in a very similar way. It's just that the signs are switched a little bit. And that's the only difference between their factorizations. All right, what would be some perfect squares? Well, the perfect square of 1 is 1. The perfect square of 2 is 4. Perfect square of 3 is 9. The perfect square of 4 is 16. The perfect square of 5 is 25. These are all examples of perfect squares. Perfect square of 6 would be 36. Perfect square of 7 is 7 times 7, 7 or 49. Perfect square of 8 is 8 times 8 is 64. 9 squared is 81. 100 is a perfect square of 10. So all these numbers to the right of the equal signs are called perfect squares. 121 is a perfect square of 11. 144 is a perfect square of 12. Perfect square of 13 is 169. Perfect square of 14 is 196. Perfect square of 15. 15 times 15 is 225. Perfect square of 16. 16 times 16 is 256. Perfect square of 17 is 289. 18 times 18 is going to be 361. 364, excuse me. Well, let's see if I got that right here. 289, 364. 19 squared is going to be 3. Let's see if I got 18 times 18 correct. Yeah, 324. I just want to do it. 19 times 19 is what do we want? Well, 19 times 19 is 380. Let's see, 381. Anybody? Let's see here. 19 times 19.
It's 361.
61. This is 324. 324 is perfect square of 18. 361 perfect square of 19. 20 times 20 is 400. And on this list goes forever. So these are the first 20 perfect squares here. So by being exposed to them, that might help your cause. All these numbers on the right, to the right of the equal signs are perfect squares. Now, some perfect cubes that exist. What's the perfect cube of 1?
One.
1 perfect cube of 2 is 2 times 2 times 2 or 8. 3 cubed, 3 times 3 times 3 is 27. 4 cubed, 4 times 4. 16 times 4 is 64. 5 cubed, 5 times 5 is 25 times 5 is 125. 6 cubed, 6 times 6 is 36 times 6 is 216. What's 7 cubed? 7 times 7 is 49, and 49 times 7 is 343. 8 cubed, 8 times 8 is 64, and 64 times another 8 is going to be 512. 9 cubed, 9 times 9 is 81. And 81 times 9 is going to be 729. Finally, 10 cubed. 10 times 10 times 10. What does that give you? That gives you what, 1,000? Okay. And on this goes. I don't think we have to list anymore. These are the first 10 perfect cubes there. Okay. All right. So now that we've seen some perfect squares and perfect cubes, that's going to help us to more accurately factor difference of squares or difference or sum of cubes as it is. And so let's see if we can now factor a couple of these here. So what would be x squared minus 64? Well, x squared minus 64, it's a binomial. Is it the sum of perfect squares or the sum of perfect cubes? Doesn't appear to be. Is the difference maybe of perfect squares or the difference of perfect cubes? Which one do you think?
Squares.
All right. 64 is a perfect square of what whole number?
8.
8. So you can see that x squared minus 64 is really x squared minus 8 squared. After having memorized these patterns, and I would strongly recommend that you memorize all of these, especially if you're going onwards in the mathematics. It's very wise and it's to your advantage to memorize all these. Anyways, we can see that x squared minus 8 squared is the difference of squares. And we just discovered that the factorization of such would be the product of conjugate binomials. So our a is really an x, and our b is really an 8. So I replace x with a with x and b with 8. So we'll have x plus 8 times x minus 8. And that's it, ladies and gentlemen. That is the factorization of that difference of squares. X plus 8 times x minus 8. And if you were to check your answer, it should work out. So if you were to take x plus 8 and multiply it by its conjugate, x minus 8, we get x times x is x squared. X multiplied by negative 8 is minus 8x. 8 times x is plus 8x. 8 times a negative 8 is minus 64. What happens to the 8x's though?
Cancel out.
The 8x's are gone, so we're left with x squared minus 64. So you can see that it works. This must be the correct factorization of x squared minus 64. All right. All right, let's try another one here. Difference between squares. Try to factor. Let's see here. 9a squared minus 16b squared. Might we have the difference between perfect squares? It kind of looks like maybe we do. 9a squared is a perfect square of what? What do you square to get 9a squared?
8.
3 what? 3a?
Yep.
3a times 3a is 9a squared. What do you square to get 16b squared?
4b.
4b. So you can see that we do have the difference between two squares. And since that's the case, this would factor into 3a plus 4b times 3a minus 4b. And we're done. That, ladies and gentlemen, is the factorization of the difference of those squares there. And Any questions about that? How we factor the difference between the squares there? Okay. Now let's try this one here. How about 25x squared minus 169? Does this factor? That binomial is the difference between what? Maybe perfect squares again? 25x squared. 25x squared is a perfect square of what?
5,
5 what? X? 169 is a perfect square of what?
13.
13. So you can clearly see that we have the difference between two squares. Being the case, this factors immediately into the product of conjugate binomials. First of which is maybe 5x plus 13 times the second is 5x minus 13. And we're done. That is the factorization of that difference of squares. Is this making sense how we're factoring the difference of squares here so far?
Yes.
All right, the difference
Yep.
of perfect squares. All right, now let's try this one. How about if we have x cubed minus 8, and we want to factor this? Well, we still have a binomial, we have the difference, but is it the difference of squares? Or maybe in this case, might it be the difference between cubes?
The
What is it?
difference in cubes.
Difference of cubes. All right, 8 is a perfect cube of 2. So you can see that we do have the difference between two cubes. In general, how do we factor the difference of cubes? Well, on the previous page, I indicated that the factorization of two cubes factors this way. Where our A is really an X and our B is a 2. So wherever we see an A, we drop in an X. Wherever we see a B, we drop in a 2. So this factors into X minus 2 times X squared plus 2X. Okay, plus what? Plus 2X. Plus 2 squared. What's 2 squared at the end? Our B is at 2, so 2 squared plus 4. And that's done, that's factored. So if you remember these patterns, it's going to be pretty easy to, to determine the factorization of these binomials. That's why I would recommend you probably just memorize those 4 patterns there. Okay, so the sum of squares can never be factored. Difference of squares always factors into the product of conjugate binomials. And the difference of cubes and the sum of cubes factors accordingly. So we got the difference of cubes here. Any questions how we factor the difference of these two cubes here? All right, well, let's see here. All right, how about this one here? If we have 64 plus 27 t cubed, how would this factor? Well, it's not the difference of anything because it's the sum. Is it the sum of squares or cubes? What do you think, Kelly? Sum of squares or cubes?
Cubes.
After a little thought, you'll realize hopefully that it is a sum of perfect cubes, 64 being 4 times 4 times 4, or 4 cubed. 27t cubed being rewritable as 3t cubed. 3t times 3t is 9t squared. 9t squared times 3t is 27t cubed. So you can see that we do have the sum of two cubes. Being the case, this would factor into this right here. So that's how it would factor. Our A is really a 4, and our B term is really a 3t. So wherever we see an A, we drop in a 4, and wherever we see a B, we drop in 3t. Here we go. This factors into 4 plus 3t. And that's going to get multiplied by 4 squared, which is 16, minus 4 times what? 3t. 4 times 3t, which is 12t, minus 12t, plus 3t squared. What's 3t times 3t? 3t squared. That'd be 9, what? 9t squared. And we're done. This would be the factorization right here. That's the factorization of 64 plus 27t cubed. Any questions how we did this problem here? Is this making sense so far? Sum of cubes, difference of cubes.
A little bit.
All right, the key is, like I said, these patterns, you just got to become familiar with all these patterns here. So I would strongly recommend that, you just got to become familiar with these patterns here. Okay. And once you know the patterns, it's very easy to factor things accordingly. If you don't have these patterns, if you don't memorize these patterns, it's going to be kind of difficult to know how these different types of binomials factor. All right, so it's very important to try to commit those patterns to memory. Okay. Especially if we're going to go on. Yes, go ahead.
So for your 9t squared,
Mhm.
why did we multiply that and not leave it the 3t?
For the 9t squared.
Yeah.
Yeah, 3t has to be what? It has to be squared at the end. So that would give you 9t squared. You left it unmultiplied?
Right, you're still leaving it squared though. That's why I didn't understand.
Oh, well, my B term here is what? My B is really what? 3t. So 3t has to go in here. What's 3t times 3t? 3t
Yeah.
times 3t is what? 9t squared? Because my B is 3t.
Separate from the t squared. So you're just doing the 3, right? Not the t, which is really the b.
No, B is all of this. It's 3t. B is all of this. Because that's the last term that's being cubed is 3t. Not just t, not just 3, but 3t is being cubed. You give us 27t cubed. So what goes in for B at the end is 3t here. So this is like 3t and the whole thing gets squared. So what is 3t squared?
Okay, thanks.
That's 9t squared at the end. Okay, 9t squared. B is 3t. A is 4 in this case. B is 3t. Okay.
So even after you square it, you still put the square because of the formula.
Oh, well, you got to square, even if you square this, the t is squared, right? Because t to the second power is t squared. So you got to still have the t squared there.
Okay. Yep, thanks.
3t times 3t is 9t squared. You got to have the t there. If you don't have the t, you're saying 3t squared is 9t. That's not correct. It's 9t squared. All right. So
Thank you.
let's see.
All right, well, maybe we can try another one here. Factor. All right, want to factor this binomial here. It looks like it's the difference of not squares, but the difference of, it looks like cubes again. 8x cubed is the monomial, 2x cubed. 27y cubed is the monomial, 3y and whole thing cubed. 2x times 2x times 2x is 8x cubed. 3y times 3y times 3y is 27y cubed. So we definitely have the difference between perfect cubes. And this factors into this right here. Where our a is really equal to 2x and our b is really equal to 3y. So wherever we see an a, we drop in a 2x. B is substituted with 3y. A is 2x. A is 2x, B is 3y. And B is 3y. 3y must be squared at the end. Hence, this factorization looks like it's going to be what? 2x minus 3y times, what's 2x squared? What's 2x squared? 2x times 2x.
4x squared.
All right. 4x squared. 2x times 3y is going to be 6xy. What's 3y squared? 3y times 3y.
9y squared.
Plus 9y squared. And that's it. And that would be the correct factorization of this difference of cubes then. See that? That's the factorization of the difference of this cubes. 8x cubed minus 27y cubed. So again, knowing these patterns here for these binomials is critical if you're going to have success in factoring these binomials. All right. All right, well, do you want to try a couple on your own now? Let's see if you can factor a couple of these binomials, okay? So we'll call this classwork number 2. So I'll see if you can factor these.
Is that 9x squared or cubed? Number 1.
9x squared. This is 9x squared plus 25. All right, so try those and we'll come back and look at those there.
Well, anybody get the first one factored?
I got 3x plus 5, 3x minus 5. I don't know.
All right, for the first one.
Yeah.
All right, now this is the, what is it? The sum or difference of squares,
The sum.
sum of squares. Let's see what we said about the sum of squares. What did we say about the sum of squares?
That they cannot be factored.
Cannot be factored. Yeah. Now, here's what you said. You said that that factors into 3x plus 5 times 3x minus 5.
Mhm.
When you multiply all this out, you're going to be left with 9x squared minus 25, not 9x squared plus 25.
Okay.
This is non-factorable.
So you just leave it like that?
Yeah, you cannot factor this. You can say non-factorable.
Okay.
How about 9 minus m squared? This is the difference between what? Two squares. Do you agree? 9 being a perfect square of 3, m squared a perfect square of m. So this would factor into 3 plus m times 3 minus m. Anybody get that correct?
Why did you say number 1 was non-factorable?
Because it's the sum of two squares. Sum of two squares. The sum of two squares is non-factorable. See that term?
Okay.
You can only factor the difference between squares, not the sum of squares. All right. So you can't factor 9x squared plus 25. That's not factorable. And don't think for a moment that 9x squared plus 25 factors into 3x plus 5 times 3x plus 5. That's not correct either. Because when you FOIL this out, you'd be left with 9x squared plus 30x plus 25. This is not 9x squared plus 25. So this does not factor. Okay, does not factor. This is the difference of squares, 9 being a perfect square of 3. So this factor is like this. How about this one? Anybody get this one factored? 25 minus 4x squared. How does that factor?
X 15 squared plus 2x 15 plus squared minus 2x.
Well, you're partially on the right track, but what 25 is the perfect square of what? What number?
5.
5. So 25 minus 4x squared would factor into 5 minus 2x times 5 plus 2x. Did anybody get that one correct? You could have these signs switched around. You could have the 5 plus 2x here and the 5 minus 2x here. But anybody get this one correct?
Yes.
What do we got going on here? Difference of squares or difference of cubes?
Cubes.
Cubes.
64 is a perfect cube of what whole number?
8.
8? 8 times 8 times 8 is 64?
Or
No, 64 is not 8 cubed. 64 is 4 cubed. 4 times 4 times 4 is 64. Now, how does the difference of cubes factor then? That's why it's important to memorize these patterns. Like I'm going to factors like this. That's how the difference of cubes factors always. So please try to memorize those patterns. Therefore, 64 minus y cubed is really 4 cubed minus y cubed. So our A is really a 4 and our B is really a y. So A minus B, I put in 4 minus y times 4 squared, but 4 squared is 4 times 4 is 16 plus 4 times y plus y squared. There's your answer. This is the factorization of 64 minus y cubed. Did anybody get that correct out there?
Right, that's how this difference of cubes factors into this. If you were to take the time and multiply this all back out and gather together like terms, you would discover that you would get back 64 minus y cubed. Okay. All right, y cubed plus 1. Anybody recognize this? Y cubed plus 1. Not the sum of perfect squares, but the sum of perfect
Cubes.
cubes. And how does the sum of cubes factor? Remember the factorization of this? A plus b times a squared minus ab plus b squared. That's how the sum of cubes always factors. So your a is really a y and your b is really a 1 because 1 is 1 cubed. So therefore, y cubed plus 1 would factor into y plus 1 times y squared minus 1 times y, which is minus y, plus 1 squared. 1 squared is 1. Did anybody get that one correct? That's how y cubed plus 1 factors like this. Anybody
Yes.
got it? Okay. Finally, x cubed minus 216. 216 being a perfect cube of what? Of 6. 6 times 6 times 6. So it's the difference between perfect cubes, and therefore it factors according to this difference of cubes. Your a term here is really an x, and your b is really a 6. So this would factor into x minus 6 times x squared plus 6x plus 6 squared. What's 6 squared? 36? Did anybody get that one correct?
Yes.
That's the factorization of the difference of these cubes. Okay. Again, ladies and gentlemen, the key I can't stress enough is, you want to become familiar with these patterns here, all right? Because once you know these patterns here, you're gonna know exactly how to factor these things. All right, but if you don't have these patterns, then it's anybody's guess if you're going to get these factorizations correct for these binomials. All righty. So again, try to assimilate those into your thinking. Very important. All right, the last section. Well, let's see here. The last section, ladies and gentlemen, just deals with trying to factor any type of polynomial. So in section 6.5, they're just going to give you a polynomial and they're going to say factor it completely. And so now we're going to have to just put together everything we learned in chapter 6, all the factorization skills we've amassed. And we're going to have to then be able to just do what is called general factoring. Okay. All right. Now, I cannot stress this enough. When you're performing general factoring, you need to, first of all, factor out anything from all of the terms. You always want to ask yourself if you can factor anything out of all your terms first. And that gets back to where we started this business back in 6.1, factoring out a greatest common factor out of all your terms. I do have a factoring toolbox that I will attach to Canvas. Let's see if I can go show you what it looks like and maybe go over it. So let me see if I can bring up our website here. And I did give it to my students last semester, and I will make it available for you. you're welcome to, use it, print it off, laminate it, whatever you want to do with it, but okay. So let's go see if I can find it from last semester. Factoring toolbox, ladies and gentlemen. I'll put a link on the main dashboard of our Canvas site. And let's see how this thing works. So it's called the factoring toolbox. It helps guide you along when you're looking at a polynomial and being asked to factor it. You should consider these steps as you strive to factor any sort of polynomial. Well, it's a little slow tonight. Here we go. Called a factoring toolbox, ladies and gentlemen. Step number one, when you're asked to factor a polynomial, first step you want to consider is you want to ask yourself this question: can a greatest common factor be factored out of each term? Because if you can do that, you always do that first. Notice I give you some examples. This first polynomial, you can factor 3 out of all 3 terms. You want to do that first. Second example, you can factor a 7x squared y out of both terms here. You want to do that first. If you can't do that, or if you've already done that, the next thing is, do you have a 4-term polynomial? If so, you use the grouping method to factor it. These were the order of business in section 6.1. If you have a 4-term polynomial, you group together your first and last 2 terms, factor something out of the first and last 2 terms separately, then factor out the common binomial factor. These 2 examples illustrate the grouping method for factoring a 4-term polynomial. If not, if you can't do that, if it's not a 4-termer, do you have a trinomial? Specifically, do you have a trinomial with the leading coefficient of 1? If you do, these are the easy types to factor. All you need are 2 factors of the constant term that sum up to the middle coefficient. Once you find them, you immediately factor your trinomial into the product of 2 binomials. For instance, x squared plus 5x plus 6, 2 factors of 6 that add up to 5 or sum up to 5 would be 2 and 3. So this factors immediately in x plus 2 times x plus 3. Another example, x squared minus 2x minus 24. I need 2 factors of negative 24 that sum up to negative 2, my middle coefficient. The only ones that work are negative 6 and 4. Being the case, this trinomial factors immediately in x minus 6 times x plus 4. Those are the easy types of trinomials. Those are section 6.2. If not, do you have a difficult trinomial, one where the leading coefficient is not 1? These are the kind in section 6.3. Again, I posted a video on 6.2 and 6.3. If you haven't watched it, please take some time to do so. It's on Canvas. Here's a difficult trinomial. Leading coefficient is not 1 anymore. To factor this, we start by taking the product of the leading coefficient and the constant term. 2 times 15 is 30. I then need 2 factors of 30 that sum up to 11. As it turns out, ladies and gentlemen, those factors that work are 5 and 6. The only factors of 30 that add up to 11 are 5 and 6. Now we rewrite our trinomial as an equivalent 4-term polynomial where the middle term, 11x, gets rewritten as the sum of 5x and 6x. We now have an equivalent 4-termer. We then group it to factor it. So we then group first and last two terms and then factor it from there. And we get our factorization of that difficult trinomial to be 2x plus 5 times x plus 3. If not, do you have a binomial of any sort? Do you have the difference between perfect squares? If so, it factors accordingly. Examples, x squared minus 16 would factor in x minus 4 times x plus 4. Another example, 16x to the fourth minus 25y to the sixth. The first term of which is a perfect square of 4x squared, the second term of which is a perfect square of 5y cubed, would factor into 4x squared minus 5y cubed times 4x squared plus 5y cubed, factoring the difference of squares. If not, do you have the sum of perfect squares? If so, the sum of squares is what? Non-factorable. Which ones are missing on here, ladies and gentlemen? That would be the sum and difference of perfect what? Not squares, but what?
Cubes.
Cubes. If you have the sum of cubes, a cubed plus b cubed, it factors as a plus b times a squared minus ab plus b squared. If you have the difference of cubes, a cubed minus b cubed, factors as a minus b times a squared plus ab plus b squared. Those you can pencil in on here at the bottom when you print this out. Okay, so that's called the factoring toolbox. It helps to organize your thought process when factoring any sort of polynomial. Don't forget that first question you should always ask yourself, can I factor anything out of all the terms? Because if you can, you always do that first. Okay. All right, so let's see if we can just do some general factoring now, ladies and gentlemen. We got to make sure that these are completely factored, these polynomials. That will be expected from now on. So make sure they are completely factored. If they're not, then they're not considered to be done. So let's try a couple here. Let's try to factor 3x squared minus 27. First question we ask ourselves is what? What's the first question I ask myself as I'm staring at this binomial here? What should I ask myself first?
The greatest common factor?
And what would it be? Can I factor anything out of both these terms first?
The 3?
Yeah, we got to pull the 3 out first. Don't forget to do that. So when you factor 3 out, what do you leave behind? What do I leave behind when I factor 3 out of 3x squared?
X squared.
When you factor 3 out of 27, what do you leave behind? 9? Are we done, or can this itself be further factored down? Might this be the difference between what? Squares or cubes?
Squares.
Squares. It itself has to further factor down. And it factors down further into what? What are the factorizations? What's the factorization of x squared minus 9?
X
X what?
plus 3 and x minus 3.
X3 times x plus 3 times x minus 3. You got it. That, ladies and gentlemen, is our complete factorization of this polynomial. We are done. That one's done. That's completely factored. That makes sense?
Yes.
Yeah.
Factor this one. Let's try to factor 3w cubed minus 48w. Help me factor this polynomial. What's the first question we should always ask ourselves? Factoring toolbox. What did it say? First question, always ask yourself, can we factor anything out of all the terms first? Can we? What can I factor out of both these terms?
3.
A 3 and also a what?
A W.
A w. Times, what do we leave behind after doing so?
W squared
Squared
minus 16.
minus 16. That's it, correct? Nice job. Are we done, or can this be further factored down?
Factor down.
That's the difference between squares, isn't it? 16 is a perfect square of 4. So we have to go further. Don't leave your answer like this. It's not completely factored. We got to factor this w squared minus 16 down into what? Two binomials.
W
W
minus 4 or plus 4
times W.
minus 4.
Yep, or you could have these switched. You could have the W minus 4 here and a W plus 4 here. This, ladies and gentlemen, is completely fat. Wait a minute. Isn't this the difference of squares? Isn't 4 a perfect square of 2?
Yep.
This is the difference of squares? Well, 4 is a perfect square of 2, but is W a perfect square?
No.
W is not a perfect square. This is not the difference of squares. This is completely factored. We're done. All right, so you got to know when to stop too. All right, let's see if we can try another one here. 10r cubed plus 1,250. Ladies and gentlemen, we have to factor this completely. Help me get started on this.
I got a question.
Go ahead.
The last problem you just did.
Yeah.
I'm confused on how you got.
Well, we factored 3 out of both terms because 3 divides into itself and 3 divides into 48 16 times, doesn't it? 3 times 16 is 48.
Uh-huh.
We can also factor a W out of both these terms. Both terms have at least one factor of W. So we factored 3W out. And when you factor 3W out of 3W cubed, what do you leave behind? Just W squared? Because 3W times W squared is 3W cubed. When you factor 3W out of 48W, what do you leave behind? How does this reduce? 16, just 16? Do you see that?
Yeah, I see it.
And then W squared minus 16 is the difference of what? 2 squares, isn't it? Because 16 is a perfect square of 4. So this further factors down into W plus 4 times W minus 4.
Okay.
And
I
this,
see.
this is your complete factorization. Okay. Ladies and gentlemen, can I factor anything out of both these terms first? Anything?
10.
10. Factor 10 out. And when you do that, you leave behind r cubed plus what?
125.
Just 125. Just lop off that trailing 0. There you go. Now, are we done, or can this itself be further factored down? You recognize it?
Further factored.
This is the sum of what? Not squares, but the sum of
Cubes.
cubes. Uh-oh, do we remember how to factor the sum of cubes? See, that's what's going to come down to. That's why, ladies and gentlemen, I keep coming back to this. Please try to become familiar and memorize those patterns. It's only going to be more power to you, okay? Yeah, it's the sum of cubes, and the sum of cubes factors how? Factors into a plus b times a squared plus minus, rather. That should be a squared minus. Got to get the signs right. That should be a squared minus ab plus b squared, correct? Okay. So minus ab plus b squared. And this should be minus sign. See that there? All right. So r cubed plus 125, ladies on. What's my a? My a is really an r, my b is really a 5, agree? So this r cubed plus 125 factors as r plus 5 times r squared minus r times 5, which is minus 5r, plus 5 squared, which is 25. There you go. So this has to further factor down. So you got 10 times r plus 5 times r squared minus 5.
Where are we getting the 5 from?
Oh, where are we getting the 5 from?
Yeah.
5 to the 3rd power is 125. Isn't 125 5 cubed? 5 times 5 times 5.
Oh, okay. So, okay. All right.
Yeah. So our
B is really 5, correct? Because it's 5 that's cubed to give us the 125. All right.
Oh, okay, okay. Thank you.
All right. Yeah. Does that make sense how we factor that one completely now?
Yeah,
So the thing here, ladies and gentlemen, is we're really confronted with a polynomial and we're going to be asked to completely factor them in section 6.5, okay? General factoring. So here's what I'm going to do here. Let's go to 6.5 in our textbook. And let's see if we can, so I'm going to bring up our textbook, ladies and gentlemen. Hold on a second. All right, so we're going to bring up our textbook. There it is. And we're going to go to section 6.5. Technology allowing that to happen. We'll see. All right, section 6. Wait a minute. What just happened there? What? What? Man, not this again. It's doing this silly thing again. Well, let me see if I can go to page 420. Wait a minute. Yeah, page 420. All right, so that's not working. Okay, I'll tell you what. Let's do this. On page 420, ladies and gentlemen, they give you a whole bunch of ladies and gentlemen, of polynomials to try to factor here. And they want us to factor these completely. All right. You can notice that there's all different types throughout here. You see that? All different types. Our job is to factor every one of these completely. That's what they're going to have us do. All right. So I guess I could just pick and choose some out of there unless somebody would like to see any of these done specifically. If so, let me know. Otherwise, I'll just kind of pick and choose here. So let's just see if we can try a couple of these here. X squared minus 18x plus 81. We want to factor this trinomial. First question we ask ourselves is, can we factor anything out of all three of these terms? Can we? Can I factor anything out of all these three terms here?
all right.
9? Well, 9 doesn't divide into 1x
Oh,
squared.
yeah.
No, you can't factor a 9 out of all three terms.
Mm.
So it looks like there's nothing we can factor out. So that being the case, what we're going to do is we're going to try to factor this as a trinomial, one with a leading coefficient of 1. So I need two factors of 81 that sum up to negative 18. So my product that I need is 81, and my sum that I need is going to be what? Negative 18. Now, what are factors of 81 that sum up to negative 18? Negative 1 and negative 81? Nah, those don't work. These add up to negative 82. Negative 3 and negative 27? Nah, these add up to what? Negative 30. They got to add up to negative 18. 4 don't divide in 81. 5 don't. 6 don't. 7 don't. 8 don't. 9 does. Negative 9 and negative 9. What do you think? These add up to negative 18.
Those are the ones that work. So therefore, this trinomial factor is immediately into what? X minus 9 times X minus 9? And that would be its factorization, ladies and gentlemen. We're done with that. That's done. Let's try to factor, let's see. Let's see here. Maybe. All right, let's try to factor 2a cubed b plus 6a squared b plus 2ab. Now, what can I factor out of all three of these terms here?
2 and a.
Yeah, looks like we can factor a 2 out and also an a and also a what? B? 2ab? That's the greatest common factor. And when I factor that out of all three terms, what do I leave behind? 2ab times what gives me back 2a cubed b?
A squared.
A squared. 2ab times what gives me back 6a squared b? 3a. 2ab times what gives me back 2ab? Just 1? Is that correct? I think it is, right? And we cannot further factor this trinomial down because there are no factors of 1 that sum up to 3. The only factors of positive 1 are 1 and 1. These add up to 2, not 3. So this cannot be further factored down. So we're done with that one. That one's done. Let's try the next one here. Let's see if we can factor xy plus 3x plus 4y plus 12. All right, ladies and gentlemen, how would we factor this? First question we ask ourselves is, can we factor anything out of all four terms here? And the answer is what? Can I factor anything out of all four terms?
No.
No. So can't factor anything out of all four terms. We'll use our toolbox here to help us out. So the first question fails, ladies and gentlemen. Where is my toolbox? I had it up here. And there it is. First question fails. Second question, do we have a four-term polynomial? Yes or no? That's a four-termer. So what method are we going to use? What method is this? Grouping? So what can I factor out of the first two terms?
X.
X. I leave behind y plus 3. What can I factor out of 4y and 12?
4.
4.
4, and I leave behind what? Y plus 3. Now I can factor that common binomial factor of y plus 3 out of both these terms. There it is. Times what do I leave behind in doing so?
X plus 4.
X plus 4. X plus 4 left behind. X plus 4. Done. That's your factorization of that four-term polynomial. That one's done. That warranted the grouping method. So in section 6.5, they're going to give you all different types of polynomials, and we're going to have to be ready and armed to factor any one of these. Any one of these, ladies and gentlemen, are fair game. Let's try to factor 2x squared plus 7x minus 85. How do we factor this? Well, there's nothing we can factor out of all three terms. It's not a four-termer. It is a trinomial, easy or difficult type. Looks like a difficult type. One with leading coefficient that's not 1. To factor this, we start by taking the product of the leading coefficient and the constant term. 2 times negative 85 gives us a product of what? Negative 170. And our required sum is going to be 7. So what are factors of negative 170 that add up to 7? Can anybody envision what those would be? Sometimes they just pop into your mind. You don't have to list them all out. When you get better at these, when you practice enough, Lezaman, you may not have to, you may not have to form the entire list of factors of negative 170. You might be able to just, think about what they should be, and they might just pop right in your mind as to what the factors are. But that comes with a little bit of practice. Negative 1 and 170 are factors of negative 170. 2 goes into 170. 85 times, but these don't add up to 7, not even close to 7. 3 will not divide into 170 evenly. Does 4? No. 5 will. 5 divides into 173 34 times, but these don't add up to 7. We're still a ways away. The dogs are still out searching. Does 6 go into 170? No. 7? Nope. 8? Nope. 9? Nope. 10? Negative 17 and 10, or 17 and negative 10. Which ones work? Which ones add up to 7? Which ones sum up to 7?
17, negative 10.
17 and negative 10 are the only ones that work. Do you see that, ladies and gentlemen? So therefore, these are going to help us factor this difficult trinomial. To do so, we rewrite this now as an equivalent 4-term polynomial where 7x gets split up and written as a sum of 17x and minus 10x. We are now going to group together our first and last 2 terms. Notice, since I have a minus sign that precedes my 3rd term, and I leave my minus sign outside the parentheses, I have to remember to change the sign of my last term. So it must become a plus 85 to avoid a sign mistake. Everybody see that there? Now, what can I group factor out of the first 2 terms? Just these 2.
X.
X is all we can take out. What do I leave behind? 2x plus 17. What can I factor out of the last 2 terms? Hoping to leave behind the 2x plus 17. Here's a shortcut, ladies and gentlemen. If you divide 2 into 10, 2 divided into 10 is 5. That means I must have factored out a 5 out of the last 2 terms. Let me show you that shortcut again. If you divide 2 into 10, that means 5 had to have been factored out of here to leave behind this binomial. So we can factor a 5 out. That leaves behind, sure enough, 2x plus 17. Now we can factor the 2x plus 17 out, being a common binomial factor, times what do I leave behind after doing that? X minus 5. Done. This is the factorization of that difficult trinomial. That's called the grouping method. I made a video of these that hang out in section 6.3. Ladies and gentlemen, please watch that video, how to factor difficult trinomials. Grouping method. All right, let's try another one here. A to the 4th minus 1. Ladies and gentlemen, how do I factor this?
Can't.
Can I factor anything out of both these terms? No. Is it a 4-term polynomial? No. Is it a trinomial? No. Is it a binomial of some sort? Is this some sort of a binomial? Yes. What type? Sum of squares, difference of squares, sum of cubes, or difference of cubes? What do we got going on here? What type of
Difference of-
binomial? What's that?
Difference of different, would it be differences of squares?
You are correct. It is the difference of squares because, ladies and gentlemen, a to the 4th power is the square of a squared. Isn't that true? Isn't 1 the square of itself?
you can clearly see that we do have the difference of perfect squares here. Being the case, a to the fourth minus 1 has to factor into a squared plus 1 times a squared minus 1. Are we done? Or can we further factor down any of these? Well, this is the sum of squares, which cannot further factor down, but this is the difference of squares, which needs to further factor down. So this a squared plus 1 does not get factored down any further, but this a squared minus 1 factors down further into a minus 1 times a plus 1. Now I think we're done. You cannot further factor any of these remaining factors, and so that is it. That is the complete factorization of what we started with. So what are you thinking, ladies? How many think that if I give you a polynomial, you can completely factor it down? Do you think that if you use that factoring toolbox, that you might be able to, nail it down as to how it can factor? You think you might be able to do some of these? All right, what classwork we up to now?
3.
We are classwork 3. All right, this will be your final classwork. I'm just going to give you, ladies and gentlemen, some polynomials, and I want you to try to completely factor them, okay? So now the barn door is wide open for any type of possibility here. All right, I'm just going to throw some polynomials at you, and I want you guys to try to factor these things completely. You can use your factoring toolbox if you want to use that. Well, I didn't post it yet. I'm sorry. I didn't post it yet, so I'm just going to give you some polynomials here, and I am just going to try to have you guys factor these as completely as you can get them factored. Let's see, 25.
Don't go to sleep.
Minus 7, minus 16, minus the 5th. All right. So see if you can start to factor some of these. We'll call this classwork number 3. This will be the last one.
Knock it off.
Minus 1. All right, see if you can do these, ladies. And we'll call this classwork number 3. Okay.